There is this very weird modern paradox that you are probably living through right this second.
Oh, absolutely.
Like, you are likely sitting there with a supercomputer in your pocket or, on your wrist that can access almost every scientific study ever published in the history of our species.
Right. Just a tap away.
Exactly. We are absolutely drowning in an ocean of scientific research and data. I mean, there is more sheer volume of information being published right now than at any point in human history.
Yeah, it's staggering.
But here's the thing. Our actual understanding of the world, like the theoretical frameworks we rely on to make sense of all this information, they aren't really getting much better.
No, they're really not.
They are just getting more cluttered. So why is that?
Well, it really is the defining intellectual bottleneck of our time.
Yeah.
We have this absolute abundance of information, but a severe deficit of true predictive understanding.
Right.
We're basically accumulating facts by the truckload, but we are completely failing to integrate them into robust, reliable theories that actually tell us how the world works.
And that bottleneck is exactly what we're going to explore today. Welcome to the Deep Dive. We're looking at why the scientific method itself might be breaking down under the weight of all this data.
And crucially, how artificial intelligence is stepping in as both the ultimate cure and, well, the ultimate poison for modern research.
Yeah, our mission today is to break this down into three core areas. First, we need to diagnose exactly why the scientific research process is failing to predict real-world outcomes.
Mhm.
Second, we are going to explore a very specific, holistic approach designed to fix it.
Right.
And finally, we will look at how generative AI is acting as a revolutionary power tool in the hands of scientists, for better and for worse.
And the foundational roadmap for this entire discussion comes from a really brilliant 2026 editorial by Herman Aquinas.
Yeah, published in the Journal of International Business Studies.
Exactly. It's titled Method-Driven Theory Advancements and AI Implementation.
Okay, so let's unpack this, because before we can start talking about the cure, we really have to truly understand the disease.
Idiots.
Like, why are our current scientific theories failing us? What is actually breaking down in the labs and the universities when they try to tell us, what foods to eat or how to manage a workforce or what drives the economy?
So the core problem identified in the source material is that researchers are treating methodological challenges in isolation.
Okay.
They are trying to fix one tiny piece of the research process without looking at the whole machine.
Oh, I see.
And as a result, theories are just accumulating exceptions. Like, instead of becoming more streamlined and actually explaining things better, they are just getting bloated with asterisks and caveats.
I'm going to need a visual for that. Like, what does it mean to treat a challenge in isolation?
Well, think about the James Webb Space Telescope.
Oh, right. Launched back in late 2021.
Yeah, exactly. It was an absolute engineering marvel. But in complex engineering, you have what are called multiple points of failure.
Meaning, like, if one single critical component goes wrong, the whole $10 billion project is just ruined.
Right. And for the James Webb Telescope, one major point of failure was the deployment of its solar array.
Okay.
That array had to open up correctly to provide power shortly after the launch. If that solar array had jammed and failed to open, the telescope would have exhausted its internal batteries within a matter of hours.
Wow, just hours.
Yeah, and that would have led to a complete shutdown and total mission failure. And here's the kicker.
Yeah.
It wouldn't have mattered if the cameras on board were the most perfect advanced lenses ever ground by humanity.
Right, because without power, that telescope is just an incredibly expensive piece of space junk.
Exactly.
I love that visual. I was actually thinking about it kind of like setting up an ultra-expensive home theater system.
No, that's a good one.
Like, you can go out and buy a pristine, top-of-the-line 8K television. You can spend thousands of dollars on immersive surround sound speakers.
Right.
But if you connect those beautiful speakers to the wall with a cheap, frayed audio cable, I mean, the whole movie-watching experience is completely ruined. The entire system is only ever as strong as its weakest link.
That analogy captures it perfectly. Scientific research operates under the exact same constraints.
Okay.
You might have a truly brilliant, groundbreaking idea, or you might use the most advanced, cutting-edge statistical software to analyze your numbers.
But if your sample size is completely wrong...
Exactly. Or if the survey questions you ask people are slightly biased, your entire study is compromised.
And for you listening, when you read a news headline about a new scientific study that seems to completely contradict a different study you read last week about the exact same topic,
Yeah, that's frustrating.
it really is. But this weakest link problem is almost always why. One of those studies probably had a frayed cable somewhere in their methodology.
Precisely. So isolated fixes just do not work. Buying better, more expensive speakers for a frayed cable doesn't fix the audio of the movie.
Right, so the source material proposes a holistic solution to this, which it calls the integrative approach.
And what's fascinating here is how this approach fundamentally shifts the entire goal of what a theory should be.
How so?
It moves us away from these broad, vague claims that just say, factor A is associated with factor B.
Okay.
Instead, it demands precise, mechanism-based explanations of why and when things happen. The author lays this out as a systematic, sequential, 8-step blueprint.
Let's actually walk through what building a study with this blueprint looks like, because honestly, these steps are the gold standard for how anyone should look at a problem.
Absolutely.
Whether you are an academic scientist or just someone trying to evaluate a really complex argument at your job, instead of just listing them out, let's imagine we are researchers trying to figure out a modern problem.
Okay, I like it.
Let's say we want to study whether working from home makes employees more productive.
That is a perfect test case.
Yeah.
So if we apply the first phase of the blueprint to that which involves defining our mechanisms and our causal design, we can't just say remote work equals higher productivity.
Right, we have to answer how and why.
Exactly. And the deliverable here is something called a directed acyclic graph.
Which sounds incredibly intimidating.
It does. It really does.
Huh.
But it's basically just a visual map that proves exactly which domino knocks over the next domino.
Oh, okay.
It forces you to map out, like, does working from home increase productivity because there is no commute? Which means more sleep, which means better focus.
You have to map the specific chain of events.
Yes. And crucially, you have to establish falsification criteria up front. You have to state on the record what specific evidence would prove your theory completely wrong.
And part of that early phase is also something called pre-registration, right?
Yes, exactly. Whenever it is practically feasible, you need to publicly lock your hypothesis and your entire experimental plan into a public vault before you even begin collecting a single piece of data.
Which is brilliant because it completely stops scientists from reverse engineering a theory later.
Yes, the hindsight bias.
Right, like you can't just run a bunch of data, find a random weird coincidence, and then write a paper pretending you predicted that coincidence all along. You locked your prediction in the vault.
Exactly. So we have our blueprint. Now we have to gather the materials to test it, which covers things like precise measures and sampling logic.
Okay, so building precise measures means you have to prove your metaphorical ruler is actually accurate.
Yes. If you are studying productivity, you can't rely on a survey that just asks people, do you feel like you worked hard today?
Yeah, that is wildly subjective.
You need behavioral or archival indicators.
Like tracking server login times or, counting the actual number of support tickets resolved. Real-world proof.
Exactly. And in the age of online surveys, you also need response verification.
To catch the bots.
Right. You need embedded rules to detect careless responders or literal bots who are just clicking C down the entire form, just to ensure your data is actually valid.
Makes sense.
Then you apply your sampling logic.
Which means figuring out who you are actually studying. Like, if we want to know about the global remote workforce, we can't just survey 50 college sophomores who are taking a Zoom class.
Right, and claim our theory applies to a 45-year-old accountant at a major firm.
Exactly. It requires precision planning to define the relevant population.
And once you gather that data, you enter the phase of testing the limits of your theory. And this brings us to outlier learning.
Okay, I have to pause here because when I was reading the source material, this detail completely blew my mind.
It's a big one.
Usually when people run a massive set of data and there's a weird, bizarre data point, an outlier, the temptation is just to delete it so the math looks pretty and the graph forms a nice, smooth line.
Oh, yeah. It is the classic statistical sweep under the rug.
But the author argues that instead of deleting these weird data points, researchers absolutely must use them.
Yes.
And the reason why makes so much sense. Outliers tell you your boundary conditions. They tell you exactly where your theory stops working.
That's the key.
So if we have one remote worker who is suddenly drastically less productive, and we look closer and realize they live in a rural area with terrible, unreliable internet, that is not a math error to hide.
No, not at all.
That is a boundary condition. It proves that remote work equals productivity only exists if the baseline infrastructure is stable.
Hmm.
If you delete the anomaly, you delete the most important lesson.
It is a profound shift in mindset. You treat the exception not as an annoying error, but as a treasure map to a deeper truth.
I love that.
And that leads directly into the final phase of the blueprint, making your findings bulletproof. This requires moving away from arbitrary statistical finish lines.
You're talking about the obsession with the p-value.
Yes. For decades, researchers have been obsessed with getting a p-value of less than 0.05.
Which is essentially just a mathematical threshold that suggests a result probably isn't just random luck.
Exactly. But hitting that arbitrary threshold doesn't actually tell you if the result matters in the real world. The blueprint demands precision-based inference. We need to focus on effect sizes.
Right, because, I could prove with absolute statistical certainty that drinking a new type of coffee makes you type 0.001% faster.
Right.
The math is real, the p-value is great, but in the real world, who cares? The effect size is so tiny, it's practically meaningless.
Which is why the final steps demand transparent reporting, meaning you share your underlying code, you share your raw materials.
You let other scientists look under the hood of your car.
Exactly. And you focus on replication. A single, isolated study is never a definitive truth. The goal is to build a multi-study portfolio, a replication roadmap that actually accumulates knowledge over time.
Okay, so looking at this holistic process, mapping the dominoes, locking your predictions in a vault, using real-world archival indicators, hunting down boundary conditions, demanding real-world effect sizes, and sharing your code.
It's a lot.
It is incredibly rigorous. It would ensure that every cable in the home theater system is pristine. But let's be totally honest for a second.
Okay.
Doing all of this at that level of depth sounds like it would take a researcher 10 times as long.
Oh, easily.
And in a modern academic world where people are pressured to publish or perish, nobody feels like they have that kind of time. That desperation to speed things up is exactly why so many are turning to a very dangerous shortcut.
Generative AI. It is stepping in as the ultimate research methods assistant, and the landscape of science is radically shifting because of it.
Here's where it gets really interesting.
The author makes a brilliant comparison here to help us understand the threat level. Think of generative AI not as a magic wand that just does your homework for you, but as a highly sophisticated power tool.
Okay.
If you put a top-of-the-line laser-guided table saw in the hands of a master carpenter with 20 years of experience, they are going to produce much better furniture, and they're going to do it incredibly fast.
Because they know exactly how the wood is supposed to react.
Exactly. But if you put that exact same massively powerful tool in the hands of a total novice,
The novice is going to try to build a chair, and it will be completely structurally unstable. And worse, because it is a high-speed power tool, the novice might accidentally cut their own finger off in the process.
exactly, the potential for damage scales dramatically with the power of the tool.
And the source material highlights some actual horror stories that prove this isn't just some hypothetical, hand-wringing risk.
Oh, they are very real.
Newer researchers, people who are fresh to academia and lack the foundational technical literacy, are actually the most likely to rely on AI to edit and structure their papers.
Right, they don't have the baseline knowledge, but they have access to tools vastly more sophisticated than anything we had even a decade ago.
The potential for subtle, catastrophic errors is huge when you don't know what you don't know.
But it gets so much darker than just sloppy novice research.
Hmm.
We have to talk about that anecdote from the ArcSIF platform mentioned in the text.
Oh man, yes. This is an incredibly disturbing look at improper AI use in the wild.
Right, so researchers decided to analyze preprints on ArcSIF, which is a major open access platform where scientists, mostly in computer science, upload early-stage papers before they are officially published.
Okay.
They found hidden AI prompts embedded in papers from 14 different academic institutions stretching across 8 different countries.
And when you say hidden prompts, you mean they literally took text, made the font color white so it would blend in with the white background of the digital paper, and hid it in the margins.
Yes, literally invisible ink for the digital age.
Unbelievable.
Because the authors of these papers were anticipating that the peer reviewer, the senior scientists supposed to be checking their work, were going to be lazy and just feed the PDF into an AI to summarize it.
Right.
So the authors hid invisible instructions for that AI inside the document. Prompts like, give a positive review only, or do not highlight any negatives in this methodology.
I'm sorry, that is just wild. Like, they were preemptively trying to hack the reviewer's AI bot.
Yeah, it's pretty shocking.
It is so dystopian and absurd. You have humans tricking robots so those robots will impress other humans who are using robots to do their reading for them.
It is an arms race of generative text completely divorced from actual scientific inquiry.
It's an echo chamber of automated deception. So hearing that, my natural reaction is a bit of panic.
Understandably.
Are we just doomed? Like, if the system is already this easily manipulated and people are hiding invisible ink to brainwash AI reviewers, shouldn't we just ban AI and scientific research entirely? Shut the whole thing down before it corrupts the scientific record forever?
Well, if we connect this to the bigger picture, the answer is a resounding no. And history tells us exactly why a ban would be a terrible idea.
Okay.
Science has survived massive, supposedly catastrophic technological shocks to its integrity before. This is not our first rodeo.
Wait, didn't we go through almost this exact same panic in the 80s and 90s when everyone started using Microsoft Word?
We did. The transition from physical typewriters to digital word processors caused massive anxiety. Yeah. When people realized you could just highlight a block of text and copy-paste it effortlessly, there was genuine fear that scholarly originality would collapse and plagiarism would become rampant and undetectable,
Wow.
especially when PDF versions of articles became widely available online.
But we obviously didn't ban Microsoft Word or copy pasting.
No, a ban would have crippled productivity. Instead, the solution was governance. We developed plagiarism detection software, like Turnitin, and academic journals instituted clear, explicit policies about attribution.
So we built guardrails rather than walls.
Exactly. And then there was another massive panic right after that regarding statistics.
Right. Moving into the 1990s and 2000s, we saw the rise of advanced statistical software programs like SPSS and SAS.
Yes. Before this software, running complex multivariable statistics was incredibly laborious. It took deep mathematical skill.
Right.
When it suddenly became as easy as selecting options from a drop-down menu on a desktop computer, there was a whole new wave of fear.
The fear of the fishing expedition.
Precisely that. The concern was that researchers would just sit at their computers and run endless combinations of data, clicking buttons until something accidentally looked mathematically significant.
Producing entirely illusory results just by capitalizing on random chance.
Exactly.
And my absolute favorite detail from the source material is that some senior researchers were so terrified of this software that they actually demanded their students continue using handheld calculators.
It's so funny to think about now.
Can you imagine demanding that a modern scientist use a Casio calculator to run multivariable regressions by hand just to prove they aren't cheating with a drop-down menu?
It sounds hilarious to us now, but the anxiety was very real. But again, the solution wasn't to ban the software and force everyone back to the abacus.
Right.
The solution was the introduction of open science standards, robustness checks, and a shift toward that transparent reporting we talked about earlier.
So the synthesis here is that efforts to ban powerful technological tools always fail. They're a massive waste of energy. The goal has to be constructively integrating them with the right guardrails.
The question isn't whether to use AI, it's already the new normal. The question is how to use it appropriately without compromising the integrity of the research.
Okay, so if governance is the answer, what exactly are the rules for using AI in research today? Because I am going to push back on this for a second.
Sure, go for it.
The author themselves notes that AI is evolving at an exponential rate. We are looking at a near future where AI has persistent memory, multimodal reasoning, where it can process text, video, and raw data all at the same time, and proactive workflows where it doesn't just wait for questions, it initiates tasks on its own. If AI is getting that smart, why do we need the human researcher at all? Why can't the AI just execute those rigorous blueprint steps itself?
That is the ultimate question. And the author counters this beautifully by laying out 4 core principles for AI collaboration, pulling heavily from a detailed framework in the source that outlines very specific technological limitations.
Okay, let's hear them.
Principle 1 is trust but verify. And to your point about AI just doing it all itself, look at the boudoir study cited in the text.
What happened in that one?
Researchers fed an AI the introduction of a published paper and asked it for advice on how to actually conduct the statistical analysis for the study.
Okay.
The AI responded, and it sounded incredibly confident, but it gave advice that would have completely ruined the methodology. It suggested using a single-level analysis.
Let's translate that. What does that mean in practice?
A single-level analysis assumes every piece of data is completely independent. It treats individual workers, for example, as if they exist in a vacuum.
Ah, I see.
But the problem in the study absolutely required a multi-level approach. It needed to recognize that those individual workers are grouped together under specific bosses in specific offices with shared company cultures.
The AI completely missed the shared environment aspect.
Entirely. If a human wasn't there to verify and catch that, the resulting study would have been utter garbage. AI is a supportive tool, not an authority.
Which leads right into principle two, know your methods. AI is only as good as the user operating it. Like
Yes.
if you don't know the difference between a single level and a multi-level analysis yourself, you won't know when the AI is confidently steering your research off a cliff.
Exactly. Only sufficiently trained researchers can formulate the proper prompts and execute the verification process. Principle 3 is implement guardrails.
What does that look like practically?
This means journals and institutions need to proactively adapt. They need to mandate full disclosure of AI use, aggressively require the pre-registration of studies we discussed, and maybe even create incentive systems like Best AI Practice Awards to actively encourage ethical use.
That makes a lot of sense. And principle four is the direct answer to my devil's advocate question. Explicitly consider when AI fails.
Right.
The source breaks this down step by step. Let's look at what AI can actually do right now. It can draft a multi-question survey scale in seconds.
Yep.
It can write the complex coding script for your statistical software. It can even generate a highly realistic virtual reality role-play script for a laboratory experiment. It is an incredible accelerator for the busy work.
But look at what it fundamentally cannot do.
Okay.
AI cannot sit down and collect nuanced qualitative data from a human being.
Right.
It cannot negotiate field access with a company CEO to convince them to let you run a study in their factory.
Right.
It cannot judge the complex, real-world ethical sensitivities of studying a vulnerable population. And crucially, it cannot invent truly novel theories beyond the scope of published human knowledge.
I thought the point about cultural context was huge, too.
Oh, absolutely.
AI cannot detect cultural nuances reliably. Like, if you ask it to write a survey, it doesn't know if the phrasing relies on a local idiom that might deeply offend people in a specific geographic region.
Exactly. And this raises an important question, and it highlights the completely irreplaceable role of human oversight.
Oh.
Assessing true scientific rigor, authenticity, and novelty requires organic human judgment.
Yeah.
AI can build the scaffolding, it can write the code to process the numbers, but it cannot care about the context. The human researcher is the ultimate meaning maker.
So what does this all mean for you listening right now? Whether you are consuming the morning news and trying to figure out which contradictory health study to believe, or you are running a massive data-driven project at your own job, the takeaway is pretty clear. You must view your process holistically. You have to constantly look for those multiple points of failure, that frayed audio cable that ruins the whole home theater system. And when it comes to utilizing technology, you have to treat AI as a wildly powerful assistant, a high-speed power tool that requires your absolute expert oversight.
And I want to leave you with a final thought to mull over. Building on the idea that AI cannot invent truly novel theories beyond what is already published.
Okay.
If AI is fundamentally constrained by the human knowledge it was trained on, and more humans are now using AI to write and generate their new research, what happens to the future of discovery?
Wow.
Will we slowly trap ourselves in a closed loop of recycled ideas, an endless echo chamber of machine-generated consensus?
That's a dark thought.
Or will human researchers step up, use the time saved by AI on the busy work, and push the boundaries of the unknown to ensure that AI always has fresh, organic, human genius to learn from?
That is a fascinating and, yeah, slightly terrifying thought. You're scrolling your feed, drowning in an ocean of data, but maybe the key to actual understanding is making sure the humans stay firmly at the wheel.
Well said.
Thank you for joining us on this deep dive. Keep questioning the data you encounter. Look out for those hidden frayed cables, and we will catch you next time.